Okay, Sridhar, you can share your slides.
Right.
So, welcome to the second day of this conference. Today, the first speaker is Sridhar Narayanan from Institute of Mathematical Sciences, Chennai, and he is going to talk on some results on the restriction problem. Sridhar.
Thank you to the organizers for this opportunity. What I'm going to talk about today is a simple result and an elegant proof that is part of a larger project that I am involved in with Joy Paul, Amritanshu Prasad, and Shraddha Srivastava. So let's just get into it. So we're all familiar with what a partition is. Just to revise, a partition of a positive integer n is a non-increasing sequence of integers whose sum is n. Right? So we're all familiar with this. Here is a partition of 5. This partition is 3, 1, and 1. Some notation that I want to introduce here is the Frobenius notation for how to write partitions. So this partition in particular is a hook partition. Hook partitions are basically L-shaped partitions. Right? And so in the Frobenius notation, I will designate this partition as 2 vertical line 2, where the first 2 is the number of cells in the first row, excluding the first one, and the second 2 is the number of cells in the first column, excluding the first one. Right? So I'm just going to use this notation through the rest of this talk. Now, the restriction problem is an open problem that deals with the restriction of representation. So we're going to work over the field of complex numbers. If you have the group GLN, then the subgroup of permutation matrices inside GLN is isomorphic to Sn. So you can take an irreducible representation of GLN, which we denote by W lambda, and you can restrict it to the symmetric group Sn. And when you do that, this irreducible representation is going to decompose into a direct sum of irreducible representations of the symmetric group. And the multiplicity of each of the irreducible representations of the symmetric group is called a restriction coefficient. Now, the restriction problem is to find a combinatorial interpretation for these coefficients. And as I said, it has long been an open problem, and there are very few results on this side of it. But we know that it is closely connected to the problem of plethysms, which I won't be getting into. So what we are going to present today is a combinatorial interpretation for the multiplicity of the sign representation of the symmetric group in the restriction of hook-shaped representations of GLN. So lambda is going to be a hook shape, and mu is going to be the column shape. And we are going to do this by interpreting certain generating functions for the moment of character polynomials. So let's break down all of the terms in that sentence, starting with what a character polynomial is. So in order to define a character polynomial, you first have to define certain basic class functions called xi. So we define xi of a permutation as the number of cycles of length I in that permutation. Right? So having defined xi and the evaluation of xi on a permutation, it makes sense also to talk about the evaluation of a polynomial in these functions xi on a permutation. And that leads us to the character polynomial. So if you have a sequence of representations of symmetric groups, so in this sequence, V1 is a representation of the symmetric group S1, V2 is a representation of symmetric group S2, etc. And if you have such a sequence, the sequence is said to have eventually polynomial character if there is a polynomial in these basic class functions xi such that eventually the value of this polynomial on a permutation is equal to the character value of Vn on that permutation. Right? So after some initial n naught for every small n greater than capital N naught, if you take the character of Vn on the permutation, it is the same as the value you get when you substitute sigma into the character polynomial p. And then p is the character polynomial associated to the sequence vn. Some common examples of spaces that have character polynomials are the lambda symmetric tensor of C raised to n when restricted to the symmetric group. So this is sim lambda as a representation of Sn, and this is the lambda alternating tensor as a representation of Sn. And this last one is this is the most important to what we are trying to do. So for every irreducible representation of GLN, the restriction to Sn has a character polynomial associated to it. Now, in the interest of time, I won't be going into the character polynomials much in this talk. So what I will do is I will directly give you the generating function associated to hook-shaped character polynomials, and then we will be interpreting those generating functions. So the moment of a character polynomial is basically the inner product of the character polynomial as a class function. So we know that a character polynomial, when you evaluate it on permutations of size n, it's a class function. So it makes sense to talk about the moment of this class function with certain other irreducible representations of Sn. In particular, you can take the moment of the character polynomial with the trivial representation, and then you get the trivial moment, which is the multiplicity of the trivial representation in the representation Vn. Similarly, you can take the moment with the sign character. So this is the multiplicity of the sign representation in the representation Vn. Right? And the last part of the setup is generating functions. The generating functions are commonly used by combinatorialists to as Wilf puts it, to hang out sequences on a clothesline or something like that. So assume you have a sequence. Usually the sequence is a sequence of positive integers. Those are the things that are of interest to combinatorial. Then the generating function that is associated with the sequence is the power series, where the coefficient of x raised to n is just the nth term of that sequence. And you can extend this sort of definition to a function which has more than one input. So suppose your function, instead of having just a single input, has s inputs, then the generating function associated to that is the power series in several variables, where the coefficient of x1 raised to n1, x2 raised to n2, up to xs raised to ns is simply the function f evaluated at n1, n2 up through ns. And the reason that we are interested in generating functions is because there is an underlying calculus on the combinatorial objects, such that when you add or you multiply or do various such operations on the generating function, there are actions that analogously act on the combinatorial objects. So the study of generating functions enables us to build, in some sense, more complex combinatorial objects from simpler combinatorial objects. Right. So these are all of the parts of the setup. So we are going to basically interpret the generating functions associated to character polynomials. And as I said, we'll directly start with the generating functions. So let's fix some notation here. The generating function, the character polynomial of an irreducible representation of the general linear group W lambda, of course restricted to Sn. We will denote this by S lambda. Right? And similarly, the character polynomial associated to the kth symmetric tensor, we will denote by capital HK. And the character polynomial associated to the nth alternating tensor, we will denote by capital E subscript L. Just kind of how it's represented for symmetric functions, except with capital letters. Right? And this first identity we have is by the Peary identity. It's by the Peary rule. So we have that the moment of the character polynomial associated to a hook-shaped irreducible of GLN is equal to an alternating sum of the moment of a product of a certain sim k character polynomial multiplied by a wedge L something character polynomial. Right? So if you just look at this summation, you'll notice a few things. So if you consider two consecutive terms in this summation, we notice that the sign changes between the two of them, and also the value of the subscript of h increases by 1 as the value of the subscript of e decreases by 1, right? If you compare the j and the j plus 1 term, you'll notice that the subscript of h increases by 1, while simultaneously the subscript of e decreases by 1, and the sign changes. So this is something you should keep in mind, is that when you consider consecutive terms, the value of the h increases by 1 while the value of the e decreases by 1, or vice versa, and that the sign also alternates between those two consecutive terms. Right. So we are able to reduce, or not reduce, we are able to express this moment of an irreducible in terms of this alternating sign. And we have a generating function for each term in this alternating sign. So what we have here is that the moment of h k plus j plus 1 e l minus j evaluated at n is the coefficient of, so this notation stands for coefficient of, so it's the coefficient of x raised to k plus j plus 1, y raised to l minus j, z raised to n in this generating function. So a couple of things that we should note here. The subscript under h becomes the exponent of x. The subscript under e becomes the exponent of y. And this n at which you are evaluating the moment becomes the exponent of z. Right? So we're looking for this coefficient. And another thing about this generating function, of course, this generating function is going to consist of two types of terms. There are going to be terms that come from the numerator and terms that come from the denominator. Now, if you look at each term that comes from the numerator, each term will consist of a z raised to 1 because of this, and it will consist of some power of x, right, where I is greater than or equal to 0. So each term will consist of a single z term and some power of x. And all of the terms in the numerator will have a distinct exponent of x, right, because each exponent occurs once, so you can at most get each term from the numerator once. Now, if we consider the denominator, recall that the binomial expansion of 1 upon 1 minus t is 1 plus t square plus t cube, etc. And now we can regard t square as a term t occurring twice, and we can regard t cube as a term t occurring thrice, and so on. And so each term from the denominator can repeat, and it can repeat any number of times. So the terms from the denominator consist of a single power of z, so z raised to 1, a single power of y, and some exponent of x, right? Some positive power of x. And each term from the denominator can repeat. Right? So what I'm saying in particular is if you look at a monomial, x raised to a, y raised to b, z raised to n, and again recall that the exponent of x is the subscript of h, the exponent of y is the subscript of e, and the exponent of z is the n at which you're taking the moment. So if you look at any monomial that comes from this generating function, it has two types of terms. It has terms that come from the denominator. Each term that comes from the denominator has a yz term, and it has some power of x, and those powers can repeat, which is why we have less than or equal to, because they can be the same exponent. And the second type of term is terms that come from the numerator. Terms that come from the numerator have a single power of z, so z raised to 1, and they have some exponent or some power of x. And all of the terms that come from the numerator are distinct, which is why you don't have a less than or equal to here, because the exponents that you get from the numerator are all distinct. And you also have the condition that the total power of x that you have should be a. So what you have is sum all of the I1 to IB and sum all of the j's, and your total should be a. Now, how many terms come from the denominator? And if you notice, the power of y is b, and terms that contain a y come only from the denominator. Now that means there must be b terms that come from the denominator, since each term comes with a single power of y. Right? And if there are b terms that come from the denominator, each of these terms also contain a single power of z. And so there are uh, so there is a z raised to b that comes from the denominator. Right? And here the total exponent of z is n, and b of them come from the denominator, which means that n minus b of the terms must come from the numerator. Right? So we've uh, done, like, I mean, this is, I hope, a clear analysis of the types of terms that come. Building on this, we are going to represent monomials as certain diagrams. Right? So all of the monomials that contribute to some fixed power of x, fixed power of y, etc. We know that they can be expressed as a product of two types of terms, and now we are going to represent these terms as a diagram. And this we do simply by, okay, right, okay. So what we do is we just mark off the exponents of x on this vertical axis. So the first red term is x raised to 0 z. So we'll mark it in red at the 0th level. Right? This is yeah. And then the second red term is x raised to 1. So we're going to mark it in red on the 1 level. Right? So we have two bars here. Now, those are all of the terms that are in red, and remember that the red terms come from the numerator, and the green terms are coming from the denominator. So now look at the green terms. You have an x raised to 1 yz occurring twice, and this is possible because terms from the numerator, terms from the denominator can repeat. Right? So we'll mark two green lines on the 1 level. And the last green term that we have is at the 2nd level, so we'll mark that one. Right? So this is how we represent. This is how we represent a monomial as a diagram. Right? So what I mean by monomial is like each monomial that contributes to the total coefficient of that monomial. We will mark it as a diagram. And it's possible to read off all of the information from this diagram. For example, if you wanted to read a, which was the exponent of x, we would just add the total levels. Right? So this is 2 plus 1 plus 1 plus 1 plus 0. That is 5. If you wanted to read b, which is the exponent of y, then it is just the number of green lines. So it's 1 plus 1 plus 1, 3. Right? This is not a 3. And if you wanted to read n, which was the exponent of z, then it is just the total number of lines, so it's just 5. And again, I repeat that the exponent of x, which is 5, will be the subscript of h, and the exponent of y, which is 3, will be the subscript of e. Right? So that's the association between the coefficients and between the monomials and between the monomials and the diagrams. Right. So just pause for a second if there are any questions about this representation. Okay. So by representing monomials in this way, what this allows us to do is it allows us to express these coefficients here, or sorry, rather these moments here. It allows us to express these moments, these coefficients, as the cardinality of a finite set of diagrams. So in particular, what we are trying to say is if I'm trying to express this this moment here, or this exponent, this will be the set of all diagrams which have n total parts, L minus j green parts, and the sum of all of their levels is k plus j plus 1. Right? So we are now able to express each of these moments as the cardinality of a certain set of diagrams. Right? So we have basically an inclusion, exclusion sum of sets. And that just leads us to defining a sign reversing involution. So an involution is a function that is equal to its inverse. A sign reversing involution is going to take a diagram, into another diagram that occurs with the opposite side, right? And in such a way that obviously if you act on that second diagram again, you get back the original diagram because it's an involution. And uh, so what I said earlier was, if you consider consecutive terms, the value of k goes up by 1 while the value of e goes down by 1, and the sign reverses. So that's kind of a clue about what we're going to do. We're going to map a diagram into a diagram that occurs into the set consecutive to it, right, in a consecutive term. And the way we do this is we have a rule that says we consider the top level, right? So the top level here is 3, and if there are any green bars, then we raise the green bar up by 1 and we change the color of this bar to red, right? But if there are no green bars, that means there is a red bar. If there are no green bars, there's a red bar. If there are no green bars, then we push the red bar down to one level lower and we change its color to a green. So here's kind of a mnemonic that I have. So here, if you have a green bar, even if you have a red bar along with the green bar, you prefer to push up the green bar. So if you have a green bar, you push it up and change its color to a red. If you have a red bar and no green bar, then you push it down and change its color to a green. So this example is clear. We look at the top level, which is 3. It does have 2 green bars, so we are able to push up one of them to the level 4, and then we change its color to a red, right? And let's just verify that this is an involution. So if I act on this, the top level is 4. There are no green bars to push up, so we are forced to push down the red bar. We must push down the red bar to the 3rd level and change its color to a green, which gives us back our original diagram. So we are assured that it is an involution. Let's see if it's sign reversing. So what we will calculate the A value here. The A is just, as I said, is the sum of the levels. So it's 3 plus 3 plus 3 plus 1 plus 0, which is 10. Now B is the number of green bars, which is 1, 2, 3. And n is the total number of bars, but n is not going to change, so I'm not going to note down what n is. And now we will find what A and B are. But what we expect, if it is to be sign reversing, is either the value of A should fall by 1 while B rises by 1, or the value of A should rise by 1 while B falls by 1. So let's just see if that's true. The total A is just 4 plus 3 plus 3 plus 1 plus 0, which is 11. And B, which is the number of green bars, is 2. So the value of A has gone up by 1 and the value of B has gone down by 1. So this is indeed a sign reversing involution. And so as a consequence of this, what we are able to do is we are able to link each diagram to another diagram in a bijective way, and in such a way also that the other diagram, both these diagrams that are bijectively associated occur with opposite sign. So a lot of terms are just going to cancel out. Every term, so all of the, in each of these sets, we can divide the diagrams into those which have a green bar on top and those which do not have a green bar on top, right? And the diagrams that have a green bar on top get cut out with the diagrams one next to them, which have a red bar on top. And all of these intermediate terms get cut out. And what remains is, change the color. Right. What remains is this first set here. It remains because there's nothing to the left of it with which it can be cut. And also this set over here. And this doesn't necessarily occur with -1, it occurs with -1 raised to m. Right? But if you consider what this second set is, recall that the subscript of under h becomes the exponent of x, and the subscript under e becomes the exponent of y. And the exponent of y is also equal to the number of green bars. So this is saying that there are 0 green bars, and this subset of this entire set is the subset which has a green bar as its highest bar, right? So there must be a green bar occurring at the top. But if there are 0 green bars, then a green bar cannot occur at the top. So this set is empty, right? So what we have done by virtue of this sign reversing involution is we've reduced this alternating sum to a sum over a purely positive sum, right? This occurs with no sign, so this is a purely positive sum. So all we have to do is just sum all of the diagrams in this subset, in this red subset. Now, the intermediate steps between this and a combinatorial interpretation is reinterpreting these diagrams as bipartitions and then reinterpreting those bipartitions as a certain statistic on partitions. And so I'm going to skip both those steps and give you the final result, which is that the coefficient or the multiplicity of the sign representation in hook-shaped representation SKL is this sum over this set, where the set is the set of partitions of k plus n into exactly n parts. So it's the sum over this set, and it's the sum of this statistic where rem of lambda is the number of removable cells of lambda which do not lie in the first row. The first meaning the largest row. The number of removable cells of lambda which do not lie in the largest row. Right? So what we've done basically is we've expressed this multiplicity as the sum of some statistic over a finite set, which is basically a combinatorial interpretation. And as a result of this, we also can easily get a positivity condition. So we can get that if k is this multiplicity is 0 if and only if k is less than n minus l minus 1 choose 2. Right? So that's a little bit of thought goes into that, but it's easy to get all of this. And we can use a similar kind of method where we define a sign reversing involution and just count what is left over to get some other results. We can get the trivial representation in hook shapes, similar to how we got the sign representation in hook shape. And we can get the sign and trivial representations in two-row shapes. So two-row irreducibles of GLN restricted to SL. In fact, we can get the multiplicity of all hook-shaped irreducibles of Sn in two-row shapes of GLN, where the second shape has size 2. I forgot to mention that. This only holds when the second row has size 2. So here it holds when 1 or 2. So these are all of the results that we can get just by an easy manipulation of the monomial term. That's all I have for this stuff. Thank you for listening.
Just a little.
So I can't hear what you say.
Anupam, are you saying something? We can't hear you.
Okay. Am I audible?
Yes.
Barely.
Okay. So since no one has any questions, so let's thank the speakers.
Anupam, we can't hear you.
Anupam, we couldn't hear you at all. Did you ask if there were any questions?
Yeah. Am I audible now?
Not really. Anyway, maybe since Anupam is not audible, are there any questions? Okay, I guess if there are no questions, we can thank the speaker.
Can you hear me now?
Yes, now we can hear.
Okay. Okay, sorry, Sudhir. Okay, so we can get ready with the next talk. Okay, so let's begin. Our next speaker is Simona Hatui from ISC Bangalore, and she's going to talk on monomial and finite dimensional projective representation of groups. Simona.
Thank you, Anupam. Yeah, thank you, the organizers, for giving me opportunity to talk here. So today I will talk on monomial and finite dimensionality of projective representations of groups. So this is a joint work with Pooja Singla and E.K. Narayanan. So I will start with the definition. So what is projective representation of a group? So this is just a homomorphism from G to PGLV, where V is a complex vector space, but it can be finite dimensional or infinite dimensional also. And so this is just a homomorphism from G to this PGLV, which is this GLV cosenting by the scalar operator, identity operator. So equivalently, you can say that a map G to GLV is a projective representation if there exists a mapping alpha such that rho x, rho y can be written in this way, and rho 1 is the identity operator. So you can see that every row is associated with a alpha, and if you see just by this property that x, y, z, and in this way, if you break these two things, you will get a relation of this alpha, and this is called two co-cycle condition. So every projective representation is associated with a map alpha which satisfy this condition, and that map alpha which satisfy this condition is called two co-cycle of G. So every projective representation is associated with a two co-cycle alpha. So we say rho is an alpha representation. So these things are parallel notion as ordinary representations. So here we are always talking about complex projective representations. And for a two co-cycle alpha, you can define a group algebra C alpha G, which is a vector space over C, and with the basis elements this, and you can define the multiplication by this alpha. So this C alpha G is called twisted group algebra. And if G is finite group, the semi-simplicity of this group algebra also happens here, like ordinary representations. And also there is a bijective correspondence between these alpha representations of G and these C alpha G modules. So whenever I will write this E-G, that is only the set of inequivalent ordinary irreducible representations of G, and this will denote that set of inequivalent irreducible alpha representations of G. So our aim, So our aim in this talk is basically to talk about these irreducible alpha representations of G. So first I will define the first tool, which is Schur multiplier, how it's relate these topics. So, okay, so this was first studied by, this projective representation was first studied by Schur. So this Schur multiplier is basically, so this is basically an abelian group which cosenting by this Z2 by B2. What is the Z2 G sister? These are all two co-cycles. So I have already defined these two co-cycles are a map from G cross G to C star such that satisfies certain condition. Okay, so these are set of two co-cycles, and this form a group under element-wise multiplication you can define. And then I am defining what is B2 G C star. These are set of all two co-boundaries of G. So these are special type of co-cycles. So if you have a map mu, then you can define a gamma mu by this mu x, mu y, mu x, y inverse, and you can check this is also a co-cycle. So these special type of co-cycles are called two co-boundary of G, and then you can make this coset. So this is called Schur multiplier of G. So what is our aim? Finding projective representation of G. What does it mean? That means you take every co-cycle alpha, two co-cycle alpha, and study this set of all inequivalent irreducible alpha representation of G. But this will tell you that don't need to take every alpha, every two co-cycle. No need to take every co-cycle. You have to take only alphas up to cohomologous. That means from this class, you can pick one alpha, and then you can talk about only those irreducible alpha representations. Because if alpha and beta are cohomologous, that means if they are same as an element in H to G sister, then you can see that they are they have the bijective correspondence. That means the beta representations of G and alpha representations of G, they have this bijective correspondence. So it's enough, and you know exactly how will the projective representation will look like if you know only one part. Okay, so that's why you just take the Schur multiplier and pick one element from each class and then study the irreducible alpha representation of G. Okay, and if alpha is trivial cocycle, that means this is cohomologous to the trivial one, then these are just the ordinary representation of G. Okay, so what happens to the cyclic group? So first example this is, so when we do this ordinary representation of cyclic group, we take this rho xy is equal to rho yx, and then you break like that. And then you see that if rho is an irreducible representation in ordinary case, then rho x is a G linear map. So by Schur lemma, you can say that rho x is one-dimensional representation. But in this case, what happens? That Schur lemma also true for projective representation, even for finite group, and even true for finitely generated groups also. So here cyclic groups means not only always finite, I am talking about infinite groups also. Okay, so if you want, this is true, right? Already G is an abelian group. But if you want this is not true. What you need for this, you need alpha xy has to be equal to alpha yx, because if you break this, you have to get this condition to apply Schur lemma. So yes, as a first step, we can prove that alpha xy is equal to alpha yx for cyclic group. So that's why we can apply Schur lemma then. So that's why rho x becomes a scalar operator. So this is one-dimensional representation, and then you can see that alpha is a co-boundary because rho is a one-dimensional representation. Okay, so for cyclic group G, we see that Schur multiplier is trivial, and the irreducible alphas are only the ordinary representations of G. Then what happened for abelian group? So for abelian group, this relation is not true at all, except cyclic group. This alpha xy is equal to alpha yx. This is not true. So that's why even the abelian groups has also not only have one-dimensional projective representation, it has a higher dimensional projective representations also. And it was studied by these authors in different point of view. So in some paper they have constructed, if you know the alpha, how to construct one alpha projective representation, and in different point of view they have studied these projective representations of abelian groups. And this will tell you how to compute Schur multiplier of abelian groups also, because if you know for cyclic group. Okay, so I'm going to define another tool. So consider a stem extension. So stem extension means A is contained inside.
Mind showing that equation again, the
Sorry?
H2? Yeah.
Yes, this one.
Yeah.
Yeah, okay, so this is for direct product of group. You can compute the Schur multiplier. Okay, so you can consider a stem extension where A is contained inside the center as well as in the commutator. So then for this stem extension, there is an Hausdorff spectral sequence. I have written only this part, which I need. There is a long exact sequence. So this is the transgression homomorphism. This is inflation homomorphism. While inflation homomorphism is just the natural map, you can see that if you have a cocycle from G cross G to C star, then you compose with G star, then you will get a cocycle here. And how the transgression is defined, you take a section from G to G star, and then you define that transgression of, if you have a homomorphism F, then XY, this F of this mu X, mu Y, mu XY inverse. So you have this section mu here. Okay, so transgression map is different in this, defined in this way. And this is the spectral sequence given here. Okay, so the another tool for for studying this projective representation is representation group. So a group G star is called representation group of G if there exists a central extension. So this is a short exact sequence where A is contained inside the center of this group. So then if the corresponding transgression is an isomorphism. So for a stem extension, you can define a transgression map from, if you have a homomorphism, you can define this transgression map here. So this transgression is an isomorphism. Then we call G star is a representation group of G. For example, you can take this abelian group Z mod PZ direction Z mod PZ, and then you take the Heisenberg group. The diagonal entries are 1, that 3 cross 3 matrices, diagonal are 1, and And right side, you have these 3 elements, and lower are 0 terms. So these Heisenberg groups, if you consider, so this is representation group of this abelian group. Okay, but why, how this connects this with projective representation? So, okay, so if G star is a finitely generated representation of group of G, then you have a bijective correspondence between this all projective representation of G and ordinary representation of G star. So if you have representation group of G, then there is bijective correspondence. Yeah, we need this condition also. This has to be finitely generated. Otherwise, we cannot apply the Schur lemma. So that's why we need that. So then you have bijective correspondence between this projective representations of G and ordinary representation of G star. Okay, and if I get time, I will tell you how one projective alpha representation corresponds to which ordinary representation, that we can talk about if we want. Okay, so what are the steps that, so for studying a projective representation of group G, so you need first Schur multiplier, then you determine the representation group of that group G, and then determine the ordinary representation of that representation group. So these are the steps. Okay, so first we will discuss the Heisenberg groups with T variants. So yeah, this is little bit generalization of Heisenberg groups. So R is a commutative ring with identity and T is an element of R. Then you define this group by the set this, and then you define the multiplication by this T and this. So you can think this as a matrices, 2n plus 1 cross 2n plus 1 matrices. So the corner element is this A, and the last column other elements are B1, B2, Bn, diagonals are 1, and the first row is C1, C2, Cn. Other entries are 0. You can, if you consider as a matrix, then for T equals to 1, that is just the matrix multiplication like this. But you can define this for any T actually. This is not defined only for T equals to 1. And if T is not invertible, this gives you different classes of groups. So these groups we are calling Heisenberg groups with T variants. And these are nilpotent groups of nilpotency class 2. So our question was how to compute Schur multiplier and find all finite dimensional projective representations of this group, and for cyclic group. Okay? And R I am taking here as n from natural number, or it's 0. So you can consider over Z. This question we Pooja Singla. Okay, so I will give little bit. So Schur multiplier part I am not giving here. So we have also computed the Schur multiplier of these groups, and also explicitly we know how the co-cycles look like. So we proved here how the projective representations happens. Okay, so for n greater than 1, if you consider this H2n plus 1 Tz Rz, then the projective representations of this group is obtained from the irreducible projective representation of this abelian group. So for n greater than 1, it's enough to study this abelian group. Okay, but for n equals to 1, we have find the representation group, this H hat RT, we have defined this in group of class 2, nilpotency group of class 2, and by handy calculation, you can also compute the ordinary representation of H hat. Those corresponds to the projective representation of this H3T Z mod RZ. Okay. So yes, so this H2n plus 1T, if you want to study the projective of this group, it's enough to study projective representation of this abelian group. So I will give the little bit description about the projective representation of abelian groups. So okay, so then it's enough to study projective representation of this abelian group. So we have given a representation group here. So you can compute this group is of nilpotency class 2. And if you want to study projective of this abelian group, it's enough to study ordinary representation of this group. But the problem is here that if your n is large, you cannot count for a fixed dimension how many ordinary representations are there. But yes, of course, for a smaller n, you can, by handy calculation, you can compute the ordinary representations here. Okay, so this is for abelian groups. Okay, so then we have tried to extend our problem to finitely generated nilpotent groups. So what we can say about finitely generated nilpotent group? So first of all, the computing Schur multiplier is a difficult task. But if you know like one group, then you can maybe compute. But for a large class of groups, you cannot compute. And another thing which we need, that existence of G star. This is the existence of representation group is known for finite, even for infinite also, but explicit computing this representation group is also a difficult task. So how we can then characterize these irreducible projective representations of finitely generated nilpotent groups? Okay, so in ordinary, I will little bit discuss about the ordinary representation case, that if G is finitely generated discrete group, that means this is not topological group, only group structure is there. So then if rho is monomial, rho is from this is a character from H to G star. Okay, so this is the monomial definition. Then, and we can see that all irreducible representation of finite nilpotent groups are monomial. And then Dan Segel gave characterization of finitely generated nilpotent monomial representation. So if G is a finitely generated nilpotent group, then every irreducible ordinary representations of G are monomial if and only if G is abelian by finite. Okay. Another characterization was given by Ike-Narayanan and Singla for ordinary representation case. So if we can define a finite weight property. So if a representation rho of G is called, has finite weight, if there exists a subgroup H of G and a character chi such that this VH chi, that rho H V act like chi H of V, this is non-trivial and finite dimensional. This is of course a subspace of V. If this is finite dimensional, then we call this rho has a finite weight. So Narayanan and Singla, they have proved if G is a finitely generated nilpotent group, then an irreducible representation pi of G is monomial if and only if it has finite weight. And this was a generalization of this Segel's result. So our question was how we can characterize the projective monomial representations. So answer of our question that, so we have defined here also we have defined the finite weight property. Okay, so an alpha representation rho we said this has finite weight if there exists a subgroup H and an alpha representation. Okay, so we are starting with alpha representation. So we need here not only, so this is not a character, this is alpha representation psi, such that the space that rho H act as psi is non-trivial finite dimensional space. And in this case also that results through like as ordinary representation case. An irreducible alpha representation rho of a finitely generated nilpotent group is monomial if and only if it has finite weight. So finite weight in the sense alpha finite weight, maybe I can say, because I'm taking here alpha representation. So you have to work on that alpha finite weight. Okay, and this proof is not very difficult, like because we know the existence of the representation group, and you can see that if a group is finitely generated nilpotent, then we can see the representation group is also finitely generated nilpotent. Okay, and then the representation group, ordinary representations was already characterized by them. So then, yeah, little bit, we have to just do some calculations, but yeah, it's like in the same way. So only the thing is that here the representation group is also finitely generated nilpotent. That's why we can do that. Okay, so now we will talk about the finite dimensionality of projective representations. So here also G is finitely generated nilpotent, but these results are also true for polycyclic groups. So we have proved for polycyclic groups. So Hall proved for ordinary representations that all irreducible representations are finite dimensional if and only if G is abelian by finite. Oh, I'm sorry, what is meant by abelian by finite? That means G has a normal abelian subgroup N such that G quotient by N is finite. So the normal abelian subgroup has finite index in G. So, all finite dimensional ordinary irreducible representations was characterized by Hall. Even this result is also true for polycyclic case. Okay, so we proved that if you take a alpha, then all irreducible alpha representations of G are finite dimensional if and only if there is a normal abelian subgroup n such that G mod n is finite group. So you need that condition G is abelian by finite, but another condition you need alpha restricted on n cross n has to be of finite order. Okay, so this result is also true for polycyclic groups. Okay, so here are two examples I have given. So you consider this Heisenberg group, discrete Heisenberg group H3Z, because we have already talked about the projective representations of G, this group. So, and in our case, we have studied finite dimensional projective representations, but let's see, it has finite dimensional projective representations or not. Yes, it has, because this group is not abelian by finite, first of all. So if not abelian by finite, then even every irreducible and projectives are not finite dimensional. There are some more infinite dimensional representations also, even projective also. And if you take R from Z and define this group, where this first component we are taking from Z mod RZ, and if you define the group operation like that, so then this group is actually abelian by finite. You can take a normal subgroup like this, and then you can see that, so by that Hall's result, that every irreducible ordinary representations are finite dimensional here. But what happens for projective? Yeah, we can actually write explicitly how the co-cycles look like for this group. And we use the Mackay's thing. Mackay has a paper where for semi-direct product of groups, you can write explicitly co-cycles. But yeah, that there are long calculations you have to do. So we know explicitly how the co-cycles look like, and we know this every co-cycles are of finite order. So we can say that every projective representations for this group are finite, has finite dimension. Okay, so I will finish here, and there are some references. And yeah, thank you.
Thank you, Sumona. Is there any question? Any question for speaker? I hope I'm audible this time. There are no questions on YouTube also. Okay, so we thank the speaker. Thank you, Sumona. There'll be a few minutes, 5-6 minutes before the next talk.
So,
Yes.
yeah, I have a question. So here, see, at some point, I mean, yeah. So there is a bijection between the ordinal representation of the representation group and the projective representation of the group itself.
Yes.
So now, here for this bijection, I just want to roughly know where is the bijectivity of transgression map used, because
Yes, yeah. So if you know projective representation of G, okay?
Yeah.
So you know, suppose rho is a projective representation of G, and you know every element of the middle group can be written as a product of the center thing and then from the G.
correct.
So here,
Sorry, I think you are cutting off. Sorry,
so you take the element A.
Is it me
No,
only,
you are
or
not audible.
everybody is having some problem? I am not able to hear.
Yes. Sumona, you are not audible.
Anupam, is it my problem or is it Sumana's problem?
Yeah, I can't also hear.
So no, my question is, it's my problem or Sumana's problem?
I think it's her problem because I also can't hear. So,
till she comes,
So,
you can tell me where, if it at all, maybe she might not
if
have.
anyone wants to discuss in a small group, you can message to Amit, and he can form a room for you, and you can go there and discuss.
Okay, I have a quick question. Till she comes back, do one of you have a reference to this? Where can I look at this projection? Karpilowski will have it, not the Schur multiplier, but projective representation. That will have it, or should have it. Is it? Amritanshu, maybe you.
Yeah, I think it should be there. Definitely, yeah.
Yeah.
Okay, she is joining back.
Hello.
Yeah, Sumana.
Yeah, I'm so sorry. Connection lost actually.
Yeah.
So Vijit
Vijay wanted to know something.
Yes,
We
yes.
still have a couple of minutes you can discuss.
So is he there?
Yes. Vijay, you are muted.
I'm here. I'm here.
Yeah. Okay. So you have this representation group and then G, and you have the centered thing. So if you want to define the ordinary representation of the middle group, so every group of the middle group can be written as a product of the central part and the element that G, and then you have the transcription. So G has a projective representation. Suppose that is alpha representation. So transcription will give you which homomorphism corresponds to alpha. Okay, so then you define this rho tilde on A into the SG. SG is the section. So A into SG is chi of A, that which chi corresponds to the alpha into rho of that SG.
This was the one you had already had a formula there in the slide.
Yes. So so you are applying chi on the central part, and because the alpha corresponds to one chi, so on the central part, and the rho you are applying on the elements of G. So that in that way, you can define ordinary representation. Yeah.
And the details are in, where can I find it? Karpilowski, is it? Where is the detail?
These things are given in the Karpilowski. Yeah, so that projective representations of finite groups, that book. Yeah.
Neha, you can maybe share your screen now.
Is it visible now?
Yes.
Yeah. Okay. So good afternoon,
Just a minute.
Yeah.
Let me introduce you.
Yeah.
Okay, our next speaker is Neha Malik. She is a student in my department here at ISO, and she is going to talk about the total Stiefel-Whitney class of an orthogonal representation of a solid. Neha.
Yeah. Hi, good afternoon, everyone, and thank you all for joining. I also specifically want to thank all the organizers for this opportunity to present our work. So as the title says, I'll be presenting about the total Stiefel-Whitney class of an orthogonal representation of SLNQ. And this is joint work with my PhD supervisor, Dr. Steven Spellon. So let me start by saying what these Stiefel-Whitney classes are and state some of their nice properties. So let's start with a finite group G, and let's take a orthogonal representation pi of that group G, then corresponding to this pi, we can associate these elements which we denote by Wi of pi, which are elements in the ith cohomology group of G in Z mod 2Z coefficients for all I from 0, 1, 2, and so on. And these Wi pi are called the Stiefel-Whitney classes of pi. Now, if we can take the sum of all these Wi pi's and we denote it by W pi, and this W pi is an element in the cohomology ring of G, again with Z mod 2Z coefficient, and this sum is called the total Stiefel-Whitney class of pi. Also, when we are talking about Stiefel-Whitney classes, we'll be only talking about coefficients in Z mod 2Z. We will only be talking about Z mod 2Z coefficients. Now, let's come to their properties. And the first one is the zeroth Stiefel-Whitney class of any orthogonal representation pi is always the unit element 1. Also, we have the first Stiefel-Whitney class. So the first Stiefel-Whitney, we know that the first cohomology group of G is isomorphic to this group of homomorphisms from G to Z mod 2Z, and W1 gives us the exact isomorphism between these two. Also, if you take any orthogonal representation pi of dimension n, and you take I greater than n, then all Wi pi is 0 for I or for all those i's. That is why this sum turns out to be something finite. Next thing I want to talk about is the naturality of these Stiefel-Whitney classes. So if you are given a group homomorphism phi from group G1 to G2 and an orthogonal representation pi of the group G2, then we can get an orthogonal representation of G1 just by composing pi and phi here, and we can get the total Stiefel-Whitney class of this composition using the total Stiefel-Whitney class of pi using this pullback map of this phi at the level of cohomology. The next property is called the Whitney product theorem. It says that if you take two orthogonal representation of a group G and if we have two orthogonal representations, then the total Stiefel-Whitney class of direct sum is the product of the Stiefel-Whitney class of individual representation. So here this cup product is the multiplication in the cohomology ring of G. And also, due to these properties, these Stiefel-Whitney classes inside ith cohomology group, these are uniquely determined. Now, once we have set up the basics, one can ask this question that if you are given a finite group G, then find the total Stiefel-Whitney class of its orthogonal representations in terms of its character values. Now, for the cyclic groups, the answer to this question is well known. But when it comes to non-abelian groups, there is not much in the literature related to the answer to this question. So in our group, we have worked out different classes of non-abelian groups and to answer this question. So the first work that I want to mention is the work of Sujit Bhalerao and Steven Spellon on the class of dihedral groups. Next is Jyotirmay Ganguly and Steven Spellon on symmetric groups. Next is Jyotirmay Ganguly and Rohit Joshi, who worked on the obstruction classes for bicyclic groups and GL2Q. By obstruction classes, I mean the first non-trivial Stiefel-Whitney class Wi pi such that I is greater than 0. Finally, we have worked out. We have tried to answer this question for the special linear groups SL and Q in the following cases. So we have worked out SL2Q for any Q, SL3Q for Q odd, and SL3Q is our base case, and we have been able to generalize some of the results to N odd and Q3 mod form. So I'll try to say a little bit about all of these. So let me start by saying I'll say some things about in the general setup. Firstly, one of the main tools that we have used in our methods are something called detection results. So let me first say what does that mean. Now, for a finite group G and a subgroup H of G, Now, corresponding to this inclusion, we have this restriction map at the level of cohomology rings. Now, if this restriction map is injective, then we say that this subgroup H detects mod to cohomology of G. Moreover, if this map is injective, image of this I star is a subgroup of the fixed points of the under the action of normalizer on this H star H. And how does these kind of detection result help our cause is that if you take a orthogonal representation pi of G, then due to naturality, this happens. Now, if I star is if I star is injective, which is due to some detection result, then we can express the total Stiefel-Whitney class of pi in terms of the Stiefel-Whitney class of its restriction to H. Now, if H is some, for example, if H turns out to be some nice subgroup, for example, cyclic group, and we know a lot of stuff in case of cyclic groups, then we can make use of that to say something about, like for example, in our case, we have done it for special linear group. Let me state one of the detection results, which is already there. So if you take H to be a subgroup of G which has odd index in G, then H detects mod to cohomology of G. For example, if you take H to be a 2-silo subgroup of G, then the 2-silo subgroup of G will detect its mod to cohomology. So we'll use this lemma again and again. So next, I'll state the detection results that we have got in the case of SLNQ for NNQ odd. So let's just set G to be our group SLNQ, and we will denote the diagonal subgroup of SLNQ by A. And obviously, this A is isomorphic to the n-1 products of these cyclic groups of order Q-1. So our detection result says that if N and Q are odd, then this diagonal subgroup detects the mod 2 cohomology of SLNQ. Moreover, if Q is 3 mod 4, then we can then we can take the 2-silo of A, of this diagonal subgroup A, which turns out to be C2n-1, because the 2-silo of Q-1 is just C2, and so we get A to be C2n-1. And due to the lemma, the odd index lemma I mentioned earlier, this A2 detects A and A detects SLNQ. So by combining these two, we can say that if N is odd and Q is 3 mod 4, this cohomology ring of this H star G, it is detected by A2, which is a comparatively very nicer group in comparison to when we work with SLNQ. So let me give a quick sketch of the proof of this detection lemma. So firstly, we can see that this GLN-1, this general linear group sits inside SLNQ in the form of this subgroup H, like this. Now, believe me when I say that the index of H in G is odd, then N and Q are odd. This is just a simple calculation using the orders of the special linear groups and the general linear groups. Now, we can use the R odd index lemma to say that this copy of GLN-1Q detects SLNQ for odd N and Q. Next, we use the famous result by Quillen, which says that the subgroup of diagonal matrices inside GLNQ detect its mod to cohomology. So this is exactly what this statement is. So DN is the subgroup of diagonal matrices, and I star is the restriction map of the inclusion, and this is an injection. Now, RA, which is the diagonal subgroup of SLNQ, it is same as DN-1. So we combine these two steps. SLNQ is detected by the copy of GLN-1, and due to Quillen, which the mod to cohomology of GLN-1 will be detected by A. So this completes the proof of the detection lemma. But the statement I made about the image of I star being inside the fixed points under the action of normalizer, due to that statement, a stronger statement holds that for Q and N odd, H star of G injects inside H star of A under this ring of invariants under the action of W, where W is the while group of G. G is SLNQ, so this W is isomorphic to SN. Now, I want to proceed with our base case SLNQ and show our method that I'll show how to use this, how we have used this detection lemma and have obtained nice results. So for now on, let G to be our SL3Q with Q 3 mod form. So we'll have similar kind of results when Q is 1 mod form, but I'll work out this case. Here the group A2, which is the Klein 4 group C2 cross C2, sits inside SL3Q like this. As this diagonal matrix, and this due to our detection lemma, we know that this subgroup A2 detects mod to cohomology of SL3Q. Now let's set up some notations. We will denote the character group of A2 by A2 cap, and the linear also the linear characters of A2 are listed like this. So this will sine 0 0 will be 1 tensor 1, sine 1 0 will be sine tensor 1, sine 0 1 will be 1 tensor sine, and sine 1 1 will be sine sine tensor sine. Now this the total Stiefel-Whitney class corresponding to any orthogonal representation pi of G, due to our detection lemma, we have this equality, and this is an element inside this cohomology ring. So now we want to understand what is the structure of this cohomology ring is, and it is well known that the cohomology ring of this Klein 4 group is isomorphic to this polynomial algebra with two generators, where V1 and V2 are where V1 is the first Stiefel-Whitney class of this sine tensor 1, and V2 is the first Stiefel-Whitney class of, sorry, there is this typo, of sine of 1 tensor sine. Yeah. Now we can also say what is this ring of invariant under the action of this while group under the action of while group of SL3 SL3Q on this ring. So one important observation that we made is the action of this while group, which is isomorphic to S3 for SL3Q. This action on this cohomology ring is same as the action of GL22 on this polynomial algebra. So now, due to this observation, we can make use of the theory of Dixon invariance, and due to that, we get this ring of invariants to be isomorphic to Z mod 2Z in these two variables, where these C20 and C21 are Dixon invariants in V1 and V2. Now, also the action of while group on H star A2 gives us this action on the character group of A2, and this is how this action works. So if you take any element G in S3, then for example, if you take G to be 1 2, then chi will go to chi of so for example, if you take so if you take G to be 1 2, then chi t will go to chi GT G inverse, that will be chi will act on A2 A1 and then A1 inverse A2 inverse by just interchanging these. Yeah. So also now under this action on the character group of A2, we have this lemma that all the non-trivial linear characters of A2 are W conjugate. Yeah. And how does this help in our cause is that if you take any pi, an orthogonal representation of G, and see its restriction to A2, then the characters of A2 which are in the same orbit, they will have same coefficient in this restriction. So that is why pi restricted to A2 comes. So all these are non-trivial characters of A2. So they will have same coefficient, this M1 in this restriction. Now we can use our Whitney product theorem for Stiefel-Whitney classes and say what W of pi is. So so due to this and using Whitney product theorem, we just get this W of sine 10 cup, W of sine 01 cup, W sine n 11 and whole raised to the power m1. Here this doesn't make any contribution because W of any of trivial character is always 1. Yeah, so now here is our final theorem that we have got. So it says that if pi is an orthogonal representation of G, then we get our total Stiefel-Whitney classes using this. So W of sine 10 is just 1 plus V1 because W1 of sine 10 was V1 and W0 of sine 10 is 1. So the total Stiefel-Whitney class will be 1 plus V1. Similarly, W of sine 01 is 1 plus V2 and W of sine 11 is 1 plus V1 plus V2. So we got this formula, but also we can do some small calculations to say what this m1, this power m1 is, and we can express this m1 in terms of the characters or character values of pi, and where this g0 is this diagonal element -1 -1 1 inside GL3. Now, similarly, we have similar kind of results for SL3Q when Q is 1 mod 4. So there, the diagonal subgroup A, isomorphic to this bicyclic group, it detects its mod to cohomology, and it is known that H star of A it turns out to be this, and this is our final result that we have got. Yeah, so here we for this result we have made use of some of the work due to Rohit Joshi and Jyotirmay Ganguly, which said that this in the total Stiefel-Whitney classes of pi, this S1 and S2 don't appear. So if you have any pi and it is this pi is such that its first and second Stiefel-Whitney classes are 0, then in the total Stiefel-Whitney classes, this S1 and S2 don't play any role. So that is why only these T1 TIs appear here, and we have again the similar kind of character formula here. So yeah, so here this completes our work for SL3Q. Now next I want to talk about our work for SL2Q. So first, let me say what we have got for odd for SL2Q odd Q. Here, if so, let's set G to be SL2Q Q odd, and then there is a copy of quaternion group inside this G, and it appears like this. So fix any A comma B in FQ such that this happens, and yeah, such that this happens, and then Q8 sits inside SL2Q using this map. So for example, if you take Q to be 1 mod 4, then you can take A to be the iota and B to be 0. So I will go to 1 - 1 0 0. So this is like this looks like the standard the standard two-dimensional representation of the quaternion group. So, and in this case, this is the detection result that we have got, that this copy of Q8 inside G detects its mod to cohomology. And here, a nice thing to notice is that this is not dependent on Q. So for all Q, we have this nice finite group which detects its mod to cohomology. And due to its small order, we can do all the calculation nicely here. So this is our final result that we have got for the total Stiefel-Whitney classes for SL2Q Q odd. Here, the fourth cohomology group of SL2Q is just isomorphic to Z mod 2Z. We take the non-trivial element here, and the total Stiefel-Whitney class of any orthogonal representation pi is represented using this E. W pi. So anyhow, for the special linear groups, the first and second Stiefel-Whitney classes are anyway 0 for almost all of them. If W1 and W2 are 0, then we get W3 is 0 due to something called Wu's lemma. So the first non-trivial Stiefel-Whitney class that appears in this case is the fourth Stiefel-Whitney class, and that is denoted using this element E. And here also we can express this L in terms of this character formula. We can give this character formula. Now, as a corollary to this, we have, so if you take pi to be an irreducible orthogonal representation of G, then the total Stiefel-Whitney class of this irreducible orthogonal is just trivial. So we don't get anything here. So yeah, so all the higher Stiefel-Whitney classes are just 0. Now let's let's see what happens for SL2Q when Q is even. So in this case, we have this subgroup of upper unitriangular upper triangular matrices. This n n, and this n this subgroup is two Celo subgroup for G. So due to our odd index lemma, we can say that this n detects mod to cohomology of G. Yeah, and we can use this detection lemma we use this detection lemma to get our this final theorem, which says that if pi is an orthogonal representation of G, we can express the total Stiefel-Whitney class in terms of this W pi. Where a nice thing to notice here is again the appearance of Dixon invariants. So here W pi here W pi is in product of these 1 plus V, where from the again from the theory of Dixon invariants, this product is actually 1 plus summation of all the Dixon invariants. So and also again we have a character formula for this coefficient n. So yeah, so with this theorem, I would like to end my talk, and thank you all for your attention.
Thank you, Neha. Is there any question for Neha?
I have a small doubt, like perhaps I missed it. You mentioned what is the motivation behind this work?
Hello.
Any motivation behind this work? I don't know about that.
Yeah, so I think this question was in some conference. This question was raised by Dr. Dipendra Prasad, and after that, our group started working on these total Stiefel-Whitney classes. So their main use. So these are some things which come from algebraic topology. Yeah, and so and these Stiefel-Whitney classes are like are like some abstraction to some particular structures in algebraic topology. So for example, if W1 of a manifold is so these are defined for vector bundles also, and from there we use them for like we use the real vector bundle structure. We use it in our representation theory. And if, for example, if W1 of some manifold is 0, then that manifold turns out to be something orientable. And similarly, similarly, there are some other uses to these higher Stiefel-Whitney classes. So the motivation comes from the algebraic topology.
I have a question related to your answer.
Yeah.
What does it? It is in this case W1 equals 0 also means something is oriented.
Here. Yeah, I'm not sure like how to interpret W1 in terms of this representations. Yeah.
Yeah, I mean, okay, so an orthogonal representation is equivalent to a real representation, and there's a way to get like a real vector bundle out of this, and then you can, and then that answers the question of, is that real vector bundle orientable? Of course, here it just turns out to be the same as the determinant of the representation, right?
Yeah.
So orientable just means you have a reduction of the structure group to the orthogonal.
To special orthogonal, I think.
Special, yeah, special orthogonal. Yeah, thanks.
Okay, let's thank the speaker. Now we have virtual tea break. Our next session will begin in kind of 35 minutes. There'll be a break room. If you want to talk and discuss, you can go there, or you can chat here also. It's fine. If you want to join the break room, you can do that. It must be there on your screen now. Okay, so let's begin the second half of today's conference. Our next speaker is Matteo Pintonello. I hope I get his name right. From the University of the Basque Country, Spain, and he's going to talk about on the generation of verbal subgroup in profinite groups. Matteo.
Sorry. Thank you. Can you hear me?
Yes.
Yeah. Okay. Great. Yes. Yes. First of all, thank you to the organizers for this opportunity. And yes, I will talk about generation of verbal subgroups in profinite groups. So first of all, we have to define what verbal subgroups are. And okay. And if G is a group word is simply an element of a free group in n variables, x1, xn, that generate indeed this free group, and one word automatically gives a map from G to the n copies of group G to G itself, simply by substituting in all possible ways the elements of a group to the variables x1, xn. And the image of this map in general is only a set, but we denote the verbal subgroup as the generated subgroup. And sometimes we will work with abstract groups, and sometimes with profinite ones. And so if G is profinite, we will denote with the same notation actually the closure of subgroup generated by the word values, because of course we want to still be in the category of profinite groups. And actually also in profinite groups, when I will talk about generation, I will mean generation and then closure, so topological generation as usual. So really easy example is the commutator word that everybody knows, and the set of word values is simply the set of commutators, and the verbal subgroup is the derived subgroup. Slightly broader set of words are outer commutator words that are obtained by nesting commutators in different variables. So, for example, lower central words, derived words, and the first example is an outer commutator word, but the second one is not, because the variable x2 repeats once. And so these are the words, and the main problem is the one in which the question I worked on arises, is the one on conciseness. So I will give a bit of history of the problem. Let's start with an abstract group, and suppose that the set of word values is finite. Is it true that the verbal subgroup is necessarily finite? This seems a really strong condition, and well, all words that satisfy this condition are said to be concise words. And this definition was given by Philippe Paul in the 50s, who proved that many words are actually concise. And he also conjectured that all words are concise. But this conjecture was disproved by Ivanov in the 1989. He constructed a group such that a word takes a single value, a single non-trivial value, but actually the generated subgroup is infinite cyclic. And it was a pretty complicated construction using the construction of a free Bernstein group done by Olshansky, the construction of Olshansky. Anyway, it seemed to close the problem, but actually it simply moved, because there is another result of Merzliakov that said that all words are concise in linear groups. And so the problem moved from which words are concise in all groups to in which classes or groups all words are concise. And it made a lot of sense to choose the class to study as residually finite groups. One reason was that it was known that many words were concise in residually finite groups, and it was not known in general. Well, clearly, Ivanov counterexample is not residually finite. It uses the Free-Bernstein group. And in general, it seemed a really crucial and useful property. Actually, residually finite groups are really close to profinite groups. And it is really, really easy to see that all words are concise in residually finite groups, if and only if they are in profinite groups. To see this, it's really immediate, because one implication is trivial because profinite groups are residually finite. And for the other, just assume that a word W is concise in all profinite groups, and if G is a residually finite group taking where the word takes finitely many values, just embed it to the finite closure. We can do it because it's residually finite. And each word value of a profinite group can be approximated by some a sequence of elements or word values that come from GW, that come from G. And as GW is finite, it is automatically closed. So actually, all the two word values are the same, and we can conclude using the hypothesis of conciseness in profinite groups. At this point, people started working in profinite groups, as I said, and they realized that they could strengthen the conjecture, because in profinite groups, things are usually either finite or uncountable. For that reason, there is this strongly conciseness conjecture that suppose that the word values is less than 2 to the left 0. Initially, they thought countable, but continuing my hypothesis, the idea was countable. Is it true that the verbal subgroup is necessarily finite? All words that satisfy this are said to be strongly concise. And indeed, there are some words. The best result in this way is the one of a couple of years ago of Detomi, Klopsch, and Shumyatsky, who proved that outer commutator words and a few sporadic power words are strongly concise. This seems a really small class of words. So, well, and actually, we proved something more, because we also proved that if a word either implies virtual nilpotency or it is weakly rational, but I will not explain exactly what these terms means, but they are much broader classes of words. Then they are strongly concise, but we need to add an hypothesis that the verbal subgroup can be generated by finitely many word values. And this is where our question arises from. Well, to understand why that hypothesis was added, it depends on the idea, on the structure of these proofs. That is, usually we reduce from countably many word values to the verbal subgroup finitely generated in general. Then there is a second step to prove that it is finitely generated but by word values. And the last step is to prove that it is actually finite, the verbal subgroup. The first step is usually doable. Second step is a new thing. The first step is, of course, the most difficult one, but actually problems of conciseness have been studied intensively for more than 50 years. And so there is a lot of machinery known in order to pass from the second point to the third one. Instead, the second one was new. And now we get to our main question. Is it true that if a verbal subgroup is finitely generated, then it is also generated by finitely many word values? And this question has an easy answer in a few cases. For example, if the verbal subgroup is simply a Propy group, then it's immediate to realize that it's finitely generated, if and only if it is generated by word values, finitely generated by word values. This is because we simply consider the quotient by modulo of the Frattini, that is an elementary abelian group, and the set generates the verbal subgroup if and only if it generates the quotient. So from finite generating set generating set of word values, we can extract the finite one. And actually there is another case, but it's not, I mean, it's easy if we assume the theorem of Nicolas-Segal, which is really deep, which is that for lower central words, NG finitely generated profinite group, finitely generated is crucial. Then the verbal subgroup is finitely generated. If it is finitely generated, then it is also generated by finitely generated by word values. The idea is that the theorem of Nicolas-Segal assures that the abstract subgroup is closed, so coincides with a profinite subgroup with its closure, and so each generator is simply a product of finitely many word values. And now we have actually a negative answer to the main question that I remark again is it true that if a verbal subgroup is finitely generated, then it can be generated by finitely many word values? The answer is actually no. Indeed, let gamma n be any lower central word, there exists a profinite group G such that gamma n of G is procyclic for every n. And notice that by topological generation, procycling is exactly one generated, so finitely generated, but it actually cannot be generated by finitely many word values. Well, one remark is that our group G cannot necessarily be finitely generated, because otherwise it would be a contradiction with the consequence of Nicolas-Segal. So it is necessarily infinitely generated. And actually, this result relies, many results on profinite groups relies on the ones of finite groups. So the main tool is a theorem of MacDonald, which states that if G is an abstract group, and we assume its derived subgroup cyclic, then there are two cases. A positive result, which is that if G is nilpotent, or the derived subgroup is infinite, again, here, infinite as abstract group, so infinite cyclic. then the derived subgroup is generated by a single suitable commutator. But in general, for any given positive integer k, there exists a finite group k with the derived subgroup cyclic but cannot be generated by less than k commutators. From this point, it's pretty easy to understand the idea of the construction, because we just simply take this. First, it's important to understand what's the structure of these groups nk, because in order to construct this, we have to fix some odd primes, p1, pm, for m2 to the 2k minus 1. So really a lot of primes. And the groups nk is simply a semi-direct product, and it's an extension of a cyclic group of order p1 times p2 times pm, basically the product of all these primes. And on top of it, there are 2k copies of a cyclic group of order 2 acting on it. Clearly, the only thing we need to define in order to define the whole group is the action of the generators of copies of C2 onto C, the generator of a cyclic group. And the result of MacDonald assured us that through some congruency systems, and the reason why we need so many primes is that we need a lot of different congruency systems in order to apply Chinese remainder theorem and something more. And in that way, it is possible to assure that the derived subgroup is the whole cyclic group, and that for any set of less than n commutators, then these commutators generate a proper subgroup of cyclic group C. And after this, it is possible to understand the construction that we have. So firstly, we work in the case for the simple commutator world, and at that point, we just take Tk to be a product of these MacDonald groups. Our group G will simply be the inverse limit of this Tk, because of course Tk is a quotient of Tk plus 1. And to guarantee that the derived subgroup is cyclic, we anyway have to assume that all the primes, the construction of a different mk, are different. This is crucial, and it will be important also later. And at this point, it's easy to see that the derived subgroup is procyclic, simply because it's the inverse limit of the derived subgroups of all Tk, that we have constructed them in order to be cyclic. This cannot be generated by less than k commutators for any k. The idea is that simply if that was true, then it would be true also for all quotients, so in particular for mk. And if for mk, we already know that it is not true by the result of MacDonald. To generalize to different lower central words, the idea is similar, but we need to use some generalizations, some theorem of Kappa, and so on. But the idea of a basic step is really, really easy. Now, we have obtained a negative result, but as I said, we have infinitely many primes involved. If we define as P of G the set of primes dividing the order of G as a supernatural number, so I mean it would simply be the number of primes dividing the order of Q of all finite index quotients of Q. Oh, sorry, this is not order of Q, order of a quotient. Yeah. Yeah. Anyway, if in our previous case G was P of G was infinite, but we also know that if P of G is equal to 1, then we are in the case of a single P group, and we know that everything works. So a question was, if we work with finitely many primes, in which side are we? Can we find with counterexamples, or cannot we? Well, the answer, I mean, the problem was not that easy, but we have a sort of positive result under additional hypothesis, because if G is a profinite group and WG is finitely generated when with finitely many primes, And we need also pro-nilpotent, sort of similar parallelism to McDonald result. We also need nilpotency, where on the final group we only need in the verbal subgroup. Anyway, in this case, WG can be generated by finitely many word values. And the idea of this is that we take simply a slow property subgroup of a verbal subgroup. It is, we know that it is finitely generated by pro-nilpotency. And at this point, there is a normal subgroup such that basically we consider N to be the subgroup generated by all pro-P silos different from Q. And if we quotient by N, clearly we would obtain a factor group G modulo N, and its verbal subgroup is exactly Q. It's isomorphic to Q. So for that reason, Q can be generated by word values of G modulo N, because it's a verbal subgroup. But at that point, we again work as in the case of a single property group. We can extract a finite generating set consisting of word values. And we only have to check that there exists a lift of these to the big group that are still word values. But it is possible to do that, and the subgroup that these word values generate contains Q. We have now finitely many property subgroups, silo property subgroups, and each of them is generated by finitely many word values, and that is sufficient to say that the whole verbal subgroup is generated by finitely many word values. As I said, at this point, now there are still some questions open that we are still trying to understand if we can get a similar positive result, or maybe a counterexample, if we work in the case of a pro-solvable group, and of course still under the hypothesis of pi of G finite. And an interesting question is that regarding the initial problem, we also have extra hypotheses of word values to be countably many. And can we find a counterexample also in that case? This is really, really hard, because the main problem is we don't have that many examples of word values having countably many, of groups having countably many word values in a profinite group. Exactly, there is also the conjecture that if it is true, it is finite. So it is a pretty difficult problem, and we are still working on it. I'm sorry that I've been a bit faster than my rehearsal, and thank you to everybody and for this opportunity and to the organizer.
Yeah, thank you. Any question? Okay.
Just out of curiosity,
Yeah.
which kappa's result is it? Which kappa's result did you mention? LC kappa or W kappa?
No, Louis Charlotte, LC kappa.
Okay.
Yes. Yeah. Yeah. LC kappa.
Okay, thank you. This time the speaker again. We can go ahead with our next talk. John, yeah, you can share your slides.
Sure. Do you mind giving me just 1 second?
Yeah, yeah.
So would you like me to start now, or we could wait till
we can begin.
we can begin? Okay.
Yeah, you're ready.
Yes. Well,
Okay,
thanks again for inviting me. Oh, sorry. Go ahead.
Yeah, just a second. Okay, so we have our next speaker, John McHugh. I hope I pronounced his name right.
Yes.
From University of California in Santa Cruz, and he's going to talk about on the image of the trivial source ring in the ring of virtual characters of finite. John.
Well, thanks for the introduction, and thanks again for inviting me to speak. Yeah, so I'm going to talk about a problem in the modular representation theory of finite groups that my advisor, Dr. Robert Bolche, gave to me to think about a couple of years ago. Now, when I wrote this talk, I began it with a crash course on ordinary representation theory, but listening to the previous speakers, it sounds like most everyone is pretty well versed in this theory, so I can just run through the beginning of this talk pretty quickly. Throughout, G is going to be a finite group, and for now, K is a field of characteristic 0. A homomorphism like this into the general linear group of n by n matrices over K is a K representation. Representations are essentially the same as finitely generated KG modules, and so we can use module language to describe these homomorphisms. So we say a representation is irreducible if the corresponding KG module is. If you post-compose with the trace function, you get the character of the representation. Representations are equivalent if and only if their characters are equal. This is one of the nice things you get when you work over a field of characteristic 0. And the set of irreducible K characters of G is denoted like this, ir sub K of G. Some operations you can perform on representations or characters, you can add them, or you can multiply them. And then if you have a subgroup of G, you can restrict a representation or a character to H. You can go in the other direction. So if you have a subgroup H, you can induce a representation or a character to G. How that works is you take a KH module V and you just extend scalars to KG. There's another operation called inflation in the situation where you have a normal subgroup N. So if you have a representation of the quotient group, you can precompose with the canonical epimorphism to get a representation for G, and that's called the inflated representation. These operations will sort of come back into the story later on. Now here's an example computation, which again, I'm sure everyone is familiar with. Here's the quaternion group of order 8, Q8, and the subgroup structure. I'm going to show how you could use these operations to compute the character table. So we know that we always have the trivial character that's just given by the action where Q8 acts trivially on one-dimensional vector space. To get another character, an irreducible character, you could consider this quotient, which is isomorphic to a cyclic group of order 2. There's a faithful linear character from that group to the subgroup plus or minus 1 in C cross. And then inflating to Q8 gives this second irreducible character. You could do the same exact thing with this normal subgroup instead, and you get the third irreducible character. Now, you could also do that with this normal subgroup, but another way to get this fourth irreducible character is to just multiply these two, which corresponds to taking the tensor product. For the last irreducible character here, it takes a little bit more work to get your hands on it. One way to do it is to induce the linear character of the center. Again, this is cyclic of order 2, so I'm talking about the same character as I was before. Inducing that doesn't give you an irreducible character, but it gives you twice the last remaining irreducible character. This last character is going to be important to the story, so keep this in mind. There's a irreducible degree 2 character of Q8 induced from, well, it's almost induced from the center. If you multiply it by 2, then it is induced from the center. Okay, now characters can be added and multiplied, and if we allow subtraction, then we can form a ring, which I'm going to denote R sub K of G. So it's the ring of virtual characters of the group. As an abelian group, just forgetting the multiplication, it's free with a basis, the set of irreducible characters. If L is an extension of K, then I can view Rk of G as a subring of Rl of G in a natural way. Any K character is an L character. There's another important subring, at least it's important to this story. If we take L to be algebraically closed and K is still a subfield of L, I can define R bar K of G to be the subring of K valued virtual characters. So they're characters that take values in K. I've always got this containment. Now, if you're the character of a K representation, then you definitely have values in K. So I at least have this containment, but it could happen that these two things are not equal. And we'll see an example right now. So here again is the character table of Q8. So there's 5 irreducible characters, which means this group, the group of virtual characters over C, has rank 5. Now, if you just look at the table, these are all integers. So that means every irreducible character has values in Q. And so the subring of Q valued characters is just the entire ring of virtual characters. Now, the linear characters, they actually do come from representations over Q, but it turns out that chi5 doesn't. However, 2 chi5 does, and that's because, as we saw before, it's induced from a Q representation. So putting this all together, it means that the quotient R bar Q mod RQ for Q8 is isomorphic to Z mod 2Z. I mean, when you quotient, these characters sort of go away, and the only non-trivial coset here is represented by chi5, which has order 2 in this quotient group. And I boxed this because this is also going to be important to the story later on. So keep this in mind. R bar Q mod RQ for Q8 is cyclic of order 2. Okay, now here's the problem I considered. Let G be a finite group. Let P be a prime number. And now K, capital K, is going to stand for a particular field. It's Q adjoin all roots of unity that have order prime to P. So I'm gonna define a subgroup of the ring of virtual characters of G in terms of generators. What are the generators? You run over all subgroups of G, and you induce characters of the form lambda goes from H to K cross. So they're degree 1 characters where H is going into K cross. I'm gonna call this subgroup the image of kappa sub G, which is mysterious for the moment, but I'll explain where that notation comes from. So basically, I've got this subgroup of RK of G, and I want to know, when is this subgroup equal to the entire thing? Okay, so where does this problem come from? Well, it comes from modular representation theory. So for the background here, let's let O be a complete discrete valuation ring with field of fractions boldface K of characteristic 0, and a residue field lowercase k of positive characteristic P. In the literature, that triple of rings is called a P modular system. I'm going to assume that K is algebraically closed just to make the discussion easier. Okay, now a finitely generated O-free OG module is called a trivial source module if it's isomorphic to a direct summand of a permutation OG module. That's equivalent to being a direct sum of indecomposable OG modules that have trivial source. I won't explain what that means, but just for anyone who knows that terminology. Okay, so we've got this class of OG modules. And just as we constructed a ring of virtual characters for the group G, we could form a ring of virtual trivial source modules. So the elements here are basically isomorphism classes of trivial source OG modules with a sum that corresponds to a direct sum, and a product that corresponds to taking the tensor product over O. Okay, now if I take the character of a trivial source OG module, I get an element of this character ring. And so there's actually a ring homomorphism from this ring, the trivial source ring, to this virtual character ring, which is maybe a more familiar ring. Now, by a theorem of Andreas Dress, the image of kappa sub G, this ring homomorphism, is exactly the group that I defined on the previous frame. So what I'm trying to understand now is what's the image of this ring homomorphism in the virtual character ring? And I want to know, asking when is the image of kappa G equal to this thing? It's the same thing as asking when is this ring homomorphism surjective? All right, so if I want to know if kappa sub G is surjective, I might as well consider the co-kernel. And so now keep in mind, this co-kernel, it depends on the prime P that I'm working with. So we can go ahead now, and because everything is phrased in terms of characters, it's easy to just perform computations on a computer using gap, for instance. So if we set P equal to 2, I created a gap program that computes this co-kernel for all small groups. And gap produced the following table. So, of course, there are groups omitted here. I omitted any group for which the co-kernel is 0. I only included groups in this table for which the co-kernel is non-trivial. And there's something striking about this table. First of all of the output is just finite dimensional vector spaces over Z mod 2Z, if you want. So that's one observation. Another observation is that while the quaternion groups Q8, Q16, Q32, they all show up in this table. And if you study the table closely, it actually looks like these quaternion groups are playing a pretty important role, because let's take SL23, for example. This has a CeLO2 subgroup that's isomorphic to Q8. So there's a Q8 appearing in this group, just as there's a Q8 here and a Q8 here. And if you were to go through all the other groups in this table, you would find that the quaternion groups are nested in them in certain ways. They might be a subgroup, or they might be a factor group, or they might be a subsection. So that's what gap produces when P is equal to 2. Now let's move to the next prime. P is equal to 3. If we do the same computations, computing that quotient, gap doesn't find any examples. Now that doesn't mean that there aren't any, but it just means that for all small groups, I think I'd computed up to order 200. Gap couldn't find any examples where this quotient is non-zero. And in fact, I didn't try every odd prime, but looking at P equals 5, P equals 7, gap couldn't find any examples where this quotient is non-zero. So now we've got some observations, and we can use them to form some conjectures. If P is equal to 2, it looks like this quotient is always a finite dimensional vector space over F2. And in that case, P is equal to 2, it looks like the quaternion groups are playing a special role. There's some sort of rigidity to those computations. You know, it looks like Q8, Q16, Q32, those groups are all appearing in the other groups in the table. And if you look back at that table, the value of this quotient at any one of these quaternion groups is a Z mod 2Z. That might explain why Z mod 2Z is showing up everywhere else in the table. Okay, so those are two observations. The last conjecture is that if P is odd, then the image of kappa sub G is equal to the entire virtual character ring. Or that's another way of saying kappa sub G is a surjective ring homomorphism. All right, so since Q8 and Q16 seem to be playing an important role, it makes sense to sort of zoom in on what's going on for P groups. So again, P is an arbitrary prime number, and K is this special field Q adjoin the P prime roots of unity. Now here's some facts. Brouwer proved that the virtual character ring Rk of G is equal to the ring of virtual characters that have values in K. So these two rings actually coincide. They don't always for an arbitrary field of characteristic 0, as we saw before, but for this field, they do, for any finite group G. Fact number 2, if P is a P group, then Rk of P is equal to R bar K of P. So every K valued virtual character comes from a K representation. And that just follows from fact 1. What fact 2 is really saying is that this ring is the same thing as the Q valued virtual characters. And that's because K doesn't contain any roots of unity of order divisible by P. So that's not too hard to show. Now, the third fact is known as the Ritter-Segal theorem. And it says that if P is a P group, then the ring of virtual characters of QP modules is induced from characters of this form. Or, well, let me say that again. So this ring, it's generated by characters of this form. You run over all subgroups of P and you induce the trivial character. So these are just permutation representations. Now, for a P group, that's exactly equal to the image of kappa sub P. Now, putting these facts together, the quotient we're interested in computing on a P group is the same thing as this quotient, because RK of P is equal to R bar Q of P, and the image of kappa P is equal to RQ of P. So these quotients are actually equal. And this explains why in that table of computations, when we looked at the Q8 row, a Z mod 2Z was showing up. We computed in that example earlier that this quotient is isomorphic to Z mod 2Z. So now we've got an explanation for at least that first row in the table. Now here's a theorem of Roquette. Let P be a P group. If P is odd, then this quotient is always 0. R bar Q of P mod R Q of P. In other words, these two rings are equal when P is odd. But if P is even, if P is equal to 2, then this quotient might be non-zero. And if it is non-zero, then there exists subgroups S, normal and T, contained in P, such that the quotient group T mod S is isomorphic to Q8. And furthermore, the quotient is a finite dimensional vector space over F2. This is pretty striking because it seems almost like it's explaining what we were observing in that table of computations, except our table of computations was taken over all finite groups. Roquette's theorem is only in terms of a P group. And furthermore, he's considering R bar Q mod RQ, where we're considering RK mod the image of kappa. But it seems like there's a connection here. So now I want to refine my conjecture from before. The quotients that we're interested in are somehow determined by these quotients, where P runs over the class of finite P groups. I mean, it seems to match up no matter what the prime is. If P is odd, it looks like this quotient is always 0. And that's what's happening in Roquette's theorem. And the P equals 2 case seems to match up as well. But how can we make this precise? So again, this is going back to this rigidity of the table. It looks like this quotient computed at any group is determined by the computations where P is running over the finite P groups. So all of these computations are connected somehow. How can we make that precise? We do that using the language of biset functors, which was introduced by Serge Buch. Now, for time, I didn't write down the full definition of what a biset functor is or what a biset category is, but I'm going to sort of give you a vague definition of what this thing is. So first of all, a biset functor is an additive functor defined on the biset category C. Okay, this wouldn't be a very satisfactory definition if I didn't give you any more. So let me tell you what the biset category C is. The objects of this category are all finite groups. Morphisms are a little bit harder to describe, but there's 5 important types of morphisms in this category, and they're denoted like this, which is sort of suggestive how we're denoting these morphisms. But at the moment, these are just sort of abstract morphisms in this biset category. But we might call this one restriction. We might call this one induction. This one could be called inflation, deflation, and isomorphism. So what do I mean? The category C is generated by these morphisms. So these elementary morphisms, if you compose them in any possible way, and then sum those compositions, you get all the morphisms in the category. So in some
what are
sense-
the domains and codomains of these morphisms?
Good question, thanks. Yeah, so these are defined, for example, restriction. If H is a subgroup of G, then there's a morphism from G to H in the category. And if, again, in that situation, induction would be a morphism from H to G. So they kind of have the domain and the codomain that you would expect from thinking of these operations like you're used to from working in representation theory. Yeah.
Okay, I
Thanks.
get it. Thanks.
Yeah, thanks for keeping me honest. All right, so last thing I want to say, these morphisms satisfy all the relations that you would expect. And I mean, all the relations that you're familiar with from working with representation. So for example, if K is a subgroup of H, is a subgroup of G, then when you compose these morphisms, induce from K to H, and then induce from H to G, you get the induction morphism from K to G. So this is all just taking place in this category C. It's sort of like a categorical framework to base these operations in representation theory off of. Okay, it turns out that the various representation rings can be realized as biset functors. So rather than computing, for example, the virtual character ring for each group individually, you can view this thing now as a functor defined on the biset category C. And so it sort of ties all of these virtual character rings together. Now we're just thinking of one functor that's defined at any group. And so, for example, now if we think of RC as a biset functor, a functor defined on this category, if you were to plug in this morphism, induction from H to G, you would get a morphism from RC of H to RC of G, and it's exactly the morphism you think it should be. It's induction in the usual sense, induction of characters. So it turns out that this quotient that I'm interested in can be realized as a biset functor, which means, again, it's an additive functor defined on the biset category. But I can actually do a little bit better than that. So let A be an abelian group. Extending Buch's biset category, Robert Bolche and Olje Joshkun defined the A-fibered biset category, C to the A. And again, I'm going to be sort of vague here. Additive functors are now called, additive functors defined on the A-fibered biset category are called A-fibered biset functors. And the basic idea is that C to the A, it contains the original biset category C. The objects are the same. It's still all finite groups, but there's an extra type of morphism that represents multiplication by a linear A character. So it's sort of like if we work with the A-fibered biset category, we're allowed one extra operation from representation theory. You can multiply by a linear character. And so just to see what I mean with an example, remember RC, the virtual character ring, you can view that as a biset functor. Well, even better, you can view it as a C cross fibered biset functor. And if lambda is a linear character of G, then there's a morphism, which I denote multiplication with lambda, which goes from G to G in the C cross fibered biset category. So it's just an abstract morphism in this category, such that when you plug it into the functor, you get the morphism from RC of G to RC of G given by multiplication by lambda. So again, it's a larger category that allows one extra operation, the operation of multiplication by a linear character. Now, here's sort of the philosophy when working with functors, transferring from modules to functors. Additive functors should be considered as the same thing as modules. And so ideas from module theory should transfer over when you are thinking of additive functors. And one important notion you can transfer over, important to this story, is that if F is a biset functor and H is a finite group, let's let theta be an element of the image of H under F. So theta could be like a character in the virtual character ring if I took F to be RC. Set F prime of G equal to this set. What is this thing? I'm taking all of the morphisms in the biset category that go from H to G, and I'm applying them all to theta. It's kind of like generating a module. You're thinking of the homomorphisms, or the morphisms rather, as ring elements, and you're multiplying theta on the left with all of the ring elements. It's like all of the ways to carry theta from H to G. Well, then it turns out F prime is a biset functor. And if you plug in any group G into F prime, it's contained in F of G. That's clear from the definition. We say that F prime is the subfunctor of F generated by theta. So this is a way to create new biset functors from ones you already have. All right, now let's return to the problem. G is still a finite group, P is a prime number, and K is this special field. Q would join the P prime roots of unity. This quotient that I'm interested in is a K cross fibered biset functor. So now I can use this fibered biset functor language to attack my problem. And it's going to help me because, I mean, if you look back at those tables, all of the computations seem to be connected. That's explained because this thing is a fibered biset functor. So the morphisms are connecting the quotients for the different groups. And I know I went through that quickly. So if none of that made sense, here's the picture I have in mind. I'm interested in computing this quotient, and now I'm viewing it as a fibered biset functor. So it's a functor defined on the K cross fibered biset category. The objects are all of the finite groups. There's morphisms between the groups that represent the normal operations from representation theory. And I'm plugging it in, and I'm getting all of these groups, Rk of G mod the image of kappa G. These are the groups that showed up in that table. Now, in this picture, I've sort of singled out the subcategory of two groups, because the conjecture is that this quotient is sort of determined by what's going on at this lower level. At least that's what the computations in the table seem to indicate. Okay, so now we've got all the language you need to complete this problem. Let's let C sub P denote the full subcategory of the K cross fibered biset category whose objects are P groups. So it's this portion of the picture. The full subcategory whose objects are the P groups. The conjecture, now restated in this language, is that the quotient I'm interested in is determined by its restriction to that subcategory. Just like you can restrict characters to subgroups, you can restrict biset functors to subcategories. So restriction is an operation on biset functors. And just like in character theory, there's an operation that's adjoint to restriction, and it's known as induction of biset functors. So if you have a biset functor defined on this subcategory, for example, you can induce it and get a biset functor defined on the entire category. And because these operations are adjoint to one another, there's a natural transformation, eta, going from here to here. So what have I done? I take the quotient I'm interested in, I restrict it down to that subcategory, induce it back, and there's a natural transformation to the original quotient. Now, here's the main result that I was able to prove. This natural transformation is surjective. And what that means is that it's surjective in each component. If you were to plug in a group G on either side, you would get a surjective map. And from that, we can deduce everything we conjectured. So for example, we've already seen that if you compute what this quotient is at a P group, it's the same thing as computing R bar Q mod RQ. And so applying Roquette's theorem, if P is odd, we know that that quotient's 0. So that means this thing that I'm inducing is 0. If you induce the 0 biset functor, you get 0. And if that maps surjectively onto this thing, then that thing has to be 0 too. So we've done away with that conjecture. The image of kappa is equal to RK unless P is equal to 2. And in the P equals 2 case, Roquette's theorem again says that when you plug in a 2 group, you get a finite dimensional vector space over F2. So again, following that argument, if you induce that and then map it surjectively onto this thing always has to be a finite dimensional vector space over F2. Roquette's theorem also said that if P is a 2 group and this quotient is non-zero, then P has a section isomorphic to Q8. Now, there's a special theory that Buch defines, rational P biset functors. And we were able to show that in the case P is equal to 2, because this thing is a rational P biset functor, whatever that means, the restriction is generated as a biset functor by the unique nonlinear character chi5. Remember, that was the last row in the character table for Q8. So everything that's going on at that lower level in the P equals 2 case is determined by this one character. It generates everything that's going on. Well, if the restriction is generated by chi5, it's not hard to show that the induced biset functor is also generated by this character. Because this thing is surjective, that means this biset functor is generated by that character. And so we deduce that if this quotient is non-zero, then there exists subgroups S, normal, and T contained in G, such that the corresponding section is isomorphic to Q8, which was another thing we conjectured. And finally, putting it all together, it's not hard to prove that there's a detection theorem for determining when a character in RK of G is in the image of kappa. So it depends on restricting it to all subgroups H, such that H is of this form, direct product of a cyclic group of odd order and a 2 group that possesses a subquotient isomorphic to Q8. Okay, I'd like to stop there. Thanks for your attention.
Thank you, John. Any question?
May I ask a question?
Yes, of course.
So can you actually compute the dimension of is there some nice way to understand the dimension of the Z mod 2 vector space from this? I guess it reduces to the 2 groups, right?
So if you want to compute R bar Q mod RQ on a 2 group, there is a formula for that. And it uses Buch's theory of rational P biset functors. So it's determined that that rank is determined by special subgroups in the 2 group. And you can compute it based on just the subgroup structure. But to my knowledge, there's no formula for the rank of the full thing, image of kappa, or yeah, RK mod the image of kappa. I wasn't able to figure out a rank formula there. That's a good question.
Thanks. I have a very speculative question. So there was a talk earlier about Stiefel-Whitney classes and detection theorems. Do you think any of this bicep category stuff can be applied to maybe?
Well, I have to say I didn't understand everything in that talk. But I would say that biset functors are extremely useful whenever you have these operations of induction and restriction, or even if you don't have all of them, even if you only had induction and restriction, you could just consider the subcategory only containing those morphisms.
But
And
then
then
you're computing something on the representation ring, right? Some invariant of representations, and it has nice algebraic properties with respect to the representation ring.
right. So biset functors are usually considered as functors into the category of abelian groups or R modules. So if you're computing elements of an abelian group, then maybe the biset functor language wouldn't be so helpful. I think it's more helpful for computing actual groups.
And one last question. I just wanted to know, so you're defining the biset category in terms of certain morphisms, which presumably generate all the morphisms in the biset category. Are there
Right.
relations? Is it easy to formulate the relations between these morphisms?
Yeah, so actually there's two different ways to define the biset category, and I sort of gave the long version, but I shortened it. So yes, you can define the biset category by distinguishing those elementary morphisms, and then there's a list of the relations that you want them to satisfy, and those relations are exactly the ones you would guess, like restriction is transitive, induction is transitive, and so on. And if you put those relations on the category, then you can show that it exists and it's unique.
There's a Mackey relation, right? I mean, should there be something like that?
There's also a Mackey relation, yeah.
Thanks, sorry for all the
No, thank you. Yeah, if you're interested in learning more, I should have put a reference. Serge Bouc wrote a book on this entire subject called Biset Functors for Finite Groups, which I think is probably the best introduction for that material.
Thanks, I'll take it.
Any more question or comments? Okay, let's thank the speaker. Thank you, John. Okay, this concludes the session today. You are free to hang around, chat.
Thanks very much.